Welcome to the Math Record. Today we'll be learning about different types of polar graphs. This video will cover part 2 of chapter 7 of our Precalculus class. Okay, let's get started. Before we start learning about polar graphs, let's learn about some conversions first. To convert them from x, y to polar, the general form would be x would be r cosine of theta and r sine of theta. And r would be equal to x squared plus y squared, and theta would be, theta tangent of theta would be equal to y over x. But technically, we won't be using this very often because we would be dealing with x and y as variables. So this won't really have a definitive answer, like number. How do you get this? Well, think of a triangle. Imagine the triangle is like in a coordinate plane, right? So something like this. So this is at 0, 0, and this is at x. So this coordinate right here is at x, y. So if this is x and y, then the radius, which is the magnitude, would be x squared plus y squared, square root. Because of the Pythagorean theorem, because it's a right triangle, right? So that's how you get r. And then you have theta right here, basically. So, basically, sine of theta is the same thing as saying x all over, we say this is r, and this is r, equal over r. So x is the same thing as r sine, it's y over r. Then this would be, y is the same thing as r sine of theta. And the same thing could be said because cosine of theta is the same thing as x over r. So you can rewrite that as r cosine of theta is equal to x. And so that's how you get the coordinates, basically. So that's just how we're gonna be that's how the conversions will work from rectangular to polar. And also another thing we had to do before we learn about these polar graphs is we gotta learn how to do the symmetry test. Okay? So if we have an equation like r is equal to like some kind of number, like sine of theta or something, like some kind of number, there is 3 tests that we have to do. The first one is replace theta by negative theta. If the equation is the same as the equation before, then it's gonna be the graph is symmetric with the polar axes. So what does that mean? It means that basically you have a graph like this, the polar graph, be like this basically. Or sorry about the bad picture. So imagine you have a graph like this, right? Then basically what it's telling you is that if it's symmetric with the polar axes, this is the polar axis, the line, the x-axis, then basically it's gonna have another line right here because it's symmetric. And so you replace theta by like a negative theta. So imagine this, but if you put negative theta into here, you get r equals a sine of negative theta, which is the same thing as r equals negative a sine of theta using trig identities. But we won't be covering trig identities in this video. Just trust me. So basically, negative a sine of theta and sine of theta is not the same thing. So technically, it's not going to be symmetric. So basically, it's something like that. Okay. And now we have test 2, which is replace theta by pi minus theta. Because theta has to be in radians, okay? So imagine that. So we have r is equal to a sine of pi minus theta. So I'm not gonna do the property for you because you had to use trig identities, and usually this is the one that's longer. What this property tells you is that if in the polar graph, it's gonna be symmetrical with the line theta pi over 2. So technically, this is the line which is pi over 2, right? So basically, it's got to be symmetrical with that. So we have an equation like this, right? Then since if it's the same equation, basically on that, so if a sine of pi minus theta is the same thing as a sine of theta, then basically it says that this graph would be reflected across pi over 2, and because it's symmetric. That's why these are the symmetry tests. So this is what you're going to be doing. And third would be like if you replace r by negative r, or if you replace uh or if you replace theta by pi plus theta. If either one of these work, then in like this equation you substitute it in, then basically it's gonna be symmetric to the origin. So imagine you have a graph like this, right? The polar graph. Then basically, if you have a graph like uh um sorry, let's say like this, like kind of like a quadratic thing, but like a side of a quadratic, then it's gotta be related to the pole. Then it's gotta be something like this. Because the origin would be the pole. So the origin would be the right here is called the pole. This line would be called the polar axis. So the x-axis will be called the polar axis, basically. The y-axis is the line theta equals pi over 2, and the origin is called the pole. So that's basically what it is. So y-axis pi over 2, the x-axis is called the polar axis, and the origin is called the pole. So it's gonna be, so the third test tells us it's gonna be if you replace it by replace r by negative r, and it's equal to like the original equation, then it's basically going to be symmetrical to the pole. Or if you replace theta by pi plus theta, then it's going to be symmetrical to the pole. So those are the symmetry tests, and you could use them to like find out which like how graphs looks instead of like plotting like a bunch of points. So okay. Now let's actually start learning the types of graphs, the polar graphs. There are generally 6 types of polar graphs. Some other types of graphs that are like really unique that look really strange. Those are like are like not really main graphs, but it will be super specific. So for these, it's just gotta be the most general one, so you could be so you understand how polars work. For this class, it will be enough for you to understand. Usually, polar is like a subject that students really struggle on because it's really unusual to learn. So of the 6 main types of polar graphs, there are lines, circles, cardioids, limacons, lemniscates, and roses. So let's start with like the most common, which is lines. There are there are basically 3 types of lines, or generally 3 types of lines. There is the horizontal line, there is the vertical line, and there's the diagonal line. So the horizontal line uses r sine of theta, and the vertical line uses r cosine of theta, and the line and the diagonal line is just pi equals theta equals some kind of number. So a is just a number, okay? So imagine, because think about it. Let's just focus on the horizontal line, right? You have r sine of theta equals a. So r sine of theta equals a. So basically what this says is, remember the property that we set from x to y? You get you could change that into r cosine of theta, and then to, sorry, I'm running a rhyme, so I'll write it on the bottom, which is r sine of theta. So x equals r cosine of theta, and y equals r sine of theta. So if r sine of theta, which is right here, is equal to y, then basically y is equal to a. So in the regular graph, that would just look like this, right? So then that's why it works like this. That's why that's how you kind of remember the line. So think of the triangle that you use to get from x, y to r cosine theta and r sine theta. And then the same case applies to like r cosine of theta equals a. So r cosine theta right here, which is equal to x. So x is equal to a. So in the plane, it would just look like a line, right? And that's how it looks, basically. And now we're gonna have so you basically just have to find a. So you have like r sine of theta is equal to like 2. Then basically, if you're making the polar graph, then you're just gonna have to find when it's 2, basically. So it's gonna be if this is radius 1, this is radius 2, this is radius 3, then you just have to draw a line at the sorry. Then you just have to draw a vertical line at the 2 if it's r sine of theta equals 2. That's basically how you do it. I mean r cosine of theta, not sine of theta. Sorry about that. And then there is the diagonal, which says theta is equal to a. Because remember, tangent of theta is equal to y over x. And tangent could be split into using trig identities. It's basically sine of theta over cosine of theta, which is equal to y over x. So it's the same thing. Sine of theta over cosine of theta is tangent of theta. So you multiply this to here, which gets x sine of theta, and multiply cosine to the other side will be y sine of theta. Basically, we get sorry, oops, sorry, I wrote this wrong. We have tangent of theta is y over x, right? So basically, theta would be like basically the ratio between x and y. So that's why it works, because it's kind of like a slope. Because if you're looking at a graph, usually how the polar graph works is that each circle kind of represents a radius. So this is radius 1. So this would be 1, 2, 3, 4, 5. So the circles. And that's how you graph a point. So you'd be like, if you want to get a point at, because you're going to graph this in polar. So you're going to have the radius and then an angle, right? So let's say like 20 and 60 degrees, basically. So we wrote 20 and 60 degrees. What you do is that you write, I mean, not 22 and 60 degrees. You go radius 1, radius 2, and then you go 60 degrees. So there's 3 lines right here. So this is 90. So 45 is like right here. So 60 would be like around like right here. So right here. So you want to put like, a point like right here. Will be count as a out as a the 260 degrees point. And that's why it works, because basically if you have theta equals to a, then the line, let's say we have theta is equal to pi over 4. Pi over 4 is the same thing as 45 degrees. So this would be like a pi over 4, which is 45 degrees. Because this entire line is basically 45. So it would be like 0, 30, 45, 60, 90, and basically going around. Or you could just draw like other lines too. Like you could draw 72. You could just do an estimation of make a line. Like make a diagonal line. And that's how you do it. And the other cases to like make lines, it's more simple. So let's say we have some, it's kind of a little bit more complicated, I mean. Like let's say you have something like 3x plus 2y is equal to 5, right? And you want to make this line. Basically, you got to substitute in the x and y. So remember, x and y is r cosine of theta and r sine of theta. So you write 3 times r cosine of theta plus 2 r sine of theta is equal to 5. And that's basically what you had to do was for you to like get it basically in the right form. And then you kind of just get everything into r is equal to like some kind of number. So you have 2r, so you distribute out the r from both of these, so you get 3 cosine theta plus 2 sine of theta is equal to 5. And you get r is equal to 5 over 3 cosine theta plus 2 sine theta. And that will be our linear line. See, that's why it looks so weird, and you probably don't want to focus on this, but that's basically what you do. You basically use the x and y to r cosine of theta and r sine of theta to make those equations. So that's for for lines. So if you were using the symmetry test and using it for the horizontal, you're gonna see that it passes the second symmetry test because it's symmetrical to the line pi over 2. Or if you use this one because it's symmetrical to the line pi over symmetrical to the polar axes. Because think about it, you have r sine of theta is equal to a. So this one will be symmetrical to the second test, which is pi over 2. So what you technically do is that you replace pi by theta by pi minus theta. So basically you have r sine of pi minus theta is equal to a. And if you do sorry, if you do like some of the properties, it kind of just like simplifies out to r sine of theta is equal to a. This and this will be kind of equivalent. That's what they're saying. And it's kind of hard because I don't want to like show the Pythagorean identity, but if you want to look it up, you could. And then this one would be easier with just r cosine theta. So it passes the first test. So r cosine of theta, which is equal to So it has to pass the first test. So you just gonna have to think of replacing theta by theta. So you don't know if it's symmetrical. You just use the tests. You do all 3 tests. So you do, which is kind of tedious, but that's basically what polar is. So if you replace theta by negative theta, so r of cosine of negative theta is equal to a. One of the basic trig identities is the even odds identity. They say cosine of theta is the same thing as cosine of negative theta. So basically, cosine of theta would be the same thing as cosine theta. So the r are the same. So this equation would be the same as this equation. So and that's why it passes the first symmetry line test, and it gives you the symmetric property over the polar axes. So basically, that's how it works. Let's move on to the next polar graph, which talks about circles. And you basically kind of just look at it like this. So if its sine, like radius is equal to 2a sine of theta, then it's going to be over here on the top. Because think about it, sine of theta is going to be positive. If you think about this as positive, right? Because if a is positive, just think of a as positive, right? If a is positive, then you're gonna have sine of theta. It seems like it's positive, right? So it's just gonna stay positive. And then if you put a negative in front of it, then it's just gonna flip to the other side. And then cosine is usually positive also, right? So then you just gotta put positive right here. And then if it's a negative, just flip it to the other side. And that's how you basically memorize it. It's just in the form. So instead of saying like radius is equal to when you were using circles, basically, instead of saying uh, the radius times sine of theta is equal to a, you kind of move the radius. You kind of switch the radius and the a, so now it's gonna be calculating for the radius. So then the radius is gonna be changing. So you think about it. So because remember the property that the radius is equal to x squared plus y squared, and you have x y is r sine theta, x y is r cosine theta, r sine theta. So you have a case like let's say r is equal to 2a sine of theta, right? So you have this as the graph. So you think about this, you have a r square. Sorry, you have square root x squared plus y squared is equal to sine of theta. So what you do is that you multiply r by both sides. So multiply by r, and then you base r squared. You square the square root x squared plus y squared, so you get x squared plus y squared. And then you have 2a, and then r cosine of theta is the same thing as y, right? So then you subtract this to the other side. So you have x minus sorry. So you have x squared minus 2ay, plus y squared minus 2ay is equal to 0. Um, uh, okay, and then we have basically x squared, x squared plus, and then you basically put this into like the circle form, so it's y minus divide negative 2a by 2, so you get negative a squared. So that gets y squared, then minus 2a y, and then this is plus a squared. So since this it gets the two terms, you gotta minus that a squared, and then you, minus a squared is equal to 0. And then basically you move the a squared to the other side, so then it's basically equals to 2a. And then since the radius is equal, what the usual form is x squared plus y squared is equal to the radius squared. That means the radius is equal to a, and the center would be at x, which is 0, and y would be at a. So yeah, center is 0, a, and radius a. So you kind of just look at it. So 0, a, let's say our radius here was 2, right? So it's got 1, 2, and has radius 2, and it goes back. So radius at 0, 2, that means the other point is at 0, 4, and the other point is at 0, 0. And that's why it goes through that line. And that's what it looks. And it's the same, and you could do the same process for all these equations, and you get the exact same kind of like graph that looks like these. And that's basically how you do for circles. So if you want to like do conversions for those, that's basically how you like technically do it. Most of Polar is just like memorizing. So if you just know these, you basically get the general idea. I doubt teachers will actually start testing you like on this. Unless you start like majoring on this field, then you really don't need to know too much about it. But if you want the general gist, basically just know the formulas and like general form, like the equations, and you know how they look. Okay, the next one that we're gonna talk about is cardioids. The reason how do you remember that cardioids? Just remember like the cardiac system, like in your body. Cardiac would be like talking about your heart, and that's what it looks like. It looks like a heart basically, and it follows the equation radius is equal to like a plus a cosine theta, a minus a cosine theta, a plus a sine of theta, and a minus a sine of theta, basically. So it's gonna be the same term. It has to be the same number. So in the case, it'll be like radius is equal to 2 plus 2 sine of theta, something like that. So it's gotta be the same number, and it's gotta be like some kind of constant added to like this. So the difference between this and the circle is that instead you look at the circles, right? The circle doesn't have a constant. If you put 2a plus 2a sine of theta, it would technically be kind of the same to cardioids. That's how you get to cardioids. Cardioids, you just add a constant. And that kind of shifts the graph to look like a heart. So that's what it does. So, because you could kind of just think logically about it too. Because let's say you have a 2, right? And you have sine of theta. If you know your trig, basically, sine of theta could only go from -1 to 1. So if you think about it, if this is 2, right, then it can only go to -2 to 2. So basically, this is radius is either going to go from 0 to 4. So you just kind of look at the graph, right, and you look at the graph, which is 2 plus 2 sine of theta, which is right here. Then you're gonna have like as it goes around this way, right? So you're gonna have to follow the graph this way. Think about the how the rotation works. So you're gonna go at 0, 0, and then you're gonna have sine a theta, which is basic. I mean, sorry, it's gonna go around. It's not gonna start here. It's gonna start here, and it's gonna go around because it's gonna start at the polar axis, at the very start of the polar axis at the x coordinate, and then just go around, just like how I usually circle do. So it goes here. So it's gonna go positive, positive, positive. Because sine above the polar axis is positive, and it's gonna start going negative. But right? But it's gotta be calculating radius, so it's not really going negative. It's the radius that it's going like under the graph. Because you don't want to think of this graph as negative. You want to think of the graph as the distance from the point to the center, because that's saying the length of the radius. And as you go around, it's just calculating for the angles. So you're just moving it based on the angles. This is why the polar graph kind of looks weird and it's kind of hard to understand. So you kind of just go around, and then it gets the length is kind of like getting a little bigger, and it goes back down smaller, and then it gets like lower and lower, and then it goes to 0 because as it gets to kind of like 270, sine becomes sine of 270 degrees is like -1. So negative a plus a is 0, and then it kind of like goes back to the other side, and then like goes back to that graph. So that's kind of how it looks. Um, uh, and then basically the same case could be applied for here. So if you start like at this point at the circle, you kind of just go around, or you go here, and then you could just go around here, which starts right here and then goes around, and then you go here and then it starts going around. That's basically how you kind of like read the graph. So those are like sine of theta and cosine theta. Um, Similar to how the circles are like basically graphed. Like look at the circles, like sines and then negative sine and then cosine and then negative cosine. You start at the top and then you flip to the bottom because of the negative sign. Cosine starts at the positive and then flips to the other side because of the negative cosine. Sorry that it kind of looks like a little different because I put the sine over here and the cosine over here and the sine theta sine over here when I did it on the opposite side of the circle. But it basically solves the same concept. You just find where the heart shape is. So the heart shape is gonna be starting at because usually most of the graph is gonna be positive. So the positive is gonna go here and the heart goes down, and then like the heart goes back up because it flips to the other side, and then like the positive cosine goes on this side because most of the data is on the right, and then most of the data is on the left. I keep saying data, but it's not really. It's just for you how to memorize it basically. So this is how I memorize it. That you flip to the other side because of the other data. Because most of the thing is like right here. So that's how I remember the cardioids. And A also has to be positive basically. And then after cardioids we have. Sorry, let me delete this thing also. And after the sorry, actually, let me go back to circles. For circles, like you can also use those symmetry line tests, so you can find out that this passes the line power 2, this passes the line power 2, this passes the polar, and this passes the polar. Because cosine uses those even and odd identities. So basically, if you put anything with cosine when replace theta by negative theta, then it's always gonna which is the first case, then basically it's gonna be the exact same equation. Because anything like cosine theta equals cosine and negative theta. So most anything with like cosine, it's usually like gonna pass the first test, meaning it's gonna be symmetrical with the polar axes. And then you can see the same case work with cardioids, so with the cosine. See how it's cosine, cosine, and these are symmetrical with the polar axes because you see it. Because that's the reason why I usually pass this even odd identity for cosine for trig identities, and that's the reason why. Sine is a little different because sine of theta is the same thing. Sine of negative theta is the same thing as negative sine theta, so it's kind of doesn't work unless like some of these numbers could actually change it a little bit. So that's why. And then you have these that could like pass the pi over 2 because like they kind of just use another identity that works too. Now go back to limacons. Limacons, you could just um the reason I kind of could like memorize it is that limacon kind of sounds like me like a snail, so it kind of sometimes look like a snail. These pictures kind of look like it's like a cardioid, but like if you just look at the cardioids actually kind of look like a heart. Like they have a really large bend. The difference between a limacon and a cardioid is that if you look at the equation, it's A plus BI. A is not equal to B. That's basically what they're saying. If and there's two kind of limacons. There's limacons. Usually they're pronounced limacons or limacon. I usually say limacon. There's one called without loops and there's one with loops. If it's without loops, A is greater than B. And it's with loops, B is greater than A. I will if you can't memorize this, there's an easy way to think about it. But like let's now focus on the graph first without the loops. So if you think about the graphs, it has a similar concept, which using the sine and the cosine, right? So positive sign, most of the data is up. Negative the sign, most of the data is down. Um, co- uh, you have positive cosine, which most of the data on the right, and then it flips again because of negative cosine, so the data always on the left. So it seems with the same case with the width loops. So it's like most cosine, most of the right, cosine, negative cosine most of the left, and then positive sine most of the up, and then negative cosine flipped over most of the down. So basically, if you understand the general shape of how the graph for polars work, you could kind of just follow that general trend of like how it works, and then you just basically draw the equation. But sometimes you just need to look for the specific points, which I'll show later on in the video. So we have so how do you remember if it has a loops or without loops? So I'll give you the two of the cases. Let's so we have let's say 2 r equals 2 plus sorry, r equals 2 plus 3 cosine of theta, right? And you have r equals 2 I mean 3 plus 2 cosine of theta. Because it's just telling you if there's like A and B, like which one's bigger, B or A. So that's what it is. So an easy way to memorize it is that you kind of just think about only these portion of the graphs. Since cosine of theta, since like cosine of theta and sine of theta, like these graphs can only go from -1 to like the biggest value of cosine of theta and sine of theta could go to is 1, and the lowest point they could go to is -1. So you think about it, then you could just think about these. So the highest point this could go up to is a 3, and the lowest point it could go to -3. And the highest this would go to 2, and this could go to -2. So what I think about is that since this would go down to -2, this will always be positive, right? So radius will always be positive. So this one usually do not have a loop. Because if it's like positive, right? It's supposed to loop around, and there's no way for it to loop around if it's always gonna be positive. Because this is either if this is 2, that's 4, and that's 7, right? And this is -2, that's negative. I sorry, sorry. Nope, that's this is 2 and -2, right? So it's 2 goes up to 5, and it's -2 goes up to 1. So this could only go from radius 1 to radius 5. So if you just look at it, you have B is greater than A, right? I mean, yeah, you have B is greater than A. Uh, wait, no, sorry. We have sorry, it's this case where we have A is greater than B, so the constant is greater than the coefficient, which it is. So then like it's not gonna have that loop because yeah, it's always gonna be positive. You think about it, because for it to loop, it has to go around negative and then go back up as a positive, right? So it has to go around negative and go back as a positive, or it's gonna go positive and go back and then down to a negative, right? So it has to either be that positive to negative or negative to positive. So that's what it has to do, but it can't do that because it's always going to be positive, right? So it's only going to go to from 1 to 5 as the radius. But in this case, if you think about it, this goes from 3 to -3. So this could go to 5 to -1. So since this goes to negative and positive, that means it's possible for it to make a loop. And that's how I memorize it. If it could change signs, then it could it's a lemacon with a loop. It just has to have a constant plus like some kind of trig identity, which is sine or cosine. So that's how I remember about it. Because if you just think about it, you have A and B, right? And if B is bigger than A, then that means technically B could become greater than A or lower than A at some point. Because if you add them together, then basically then it's gonna have a loop. And then without loops can't do that because A is greater than B. So usually it's just gonna be positive the entire time. So it's just gonna be like look like that. It's gonna dip at some point, but they're never gonna make that loop. And that's how I basically memorize that. And basically you could just like use those symmetry tests again to like start graphing. But like that's how like you basically just use those symmetries, and that's how you just memorize. And that's for limacons. And the fifth one we're gonna talk about is roses. The reason they call it roses is that as you the general equation is r equals a cosine of theta, cosine of n times theta, which n times theta is in parentheses, and r equals a sine of theta, sine of n times theta. So the reason they're called roses is that the n actually has a really good importance. Like a is just gonna be a constant; it doesn't matter. But n is gonna be the most important factor for the roses. So the difference between these and the other graphs is that there's actually a coefficient inside of the trig function, Because like if you look for lines, right, it doesn't have one. Circles don't have one. Cardioids don't have one, and limacons don't have one. But roses have one. And what these do is that these N kind of like gives them like these petals. So as you kind of draw the graph, you look at this graph, right? So it's gonna draw a graph like this, and then go up like that, and then go back down, go here, go here, go here, go here, go here. So that's how you're gonna, and that's why they make petals. And they have these really cool properties that say that if N is even, then it's gonna have two N petals. So let's say you have R is equal to 2 cosine of 2 theta, right? Since 2 is even, that means it's going to have 2 times 2 petals, right? That's what it tells us. If it's even, it's going to have 2 times more than the n. So if this is like let's say this is like 4 theta, right? Then it's got 2 times 4, so it has 8 petals since 4 is even. And the other identity is that if the n is odd, let's say 3 theta, then it's just gonna have 3 petals. If it's like 5, then it's just gonna have 5 petals. Sorry, that looks like a 6. That's a 5. Then it's just gonna have 5 petals, basically. So it has a pretty cool like trick about that. So if you usually like the roses are the like easier ones to graph, because what I kind of usually do for these type of graphs is that, let's say we have something like this, right? Sorry, let me make this longer. Oops, sorry. Circle, 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 and another circle, right? And you're given an equation. Let's just take for example r equals like um 5 cosine of 3 pi, right? So you gotta think of when a cosine in like a unit in like an actual like a normal plane. How does that look like in how does like cosine get to its biggest value? Because I said before, the sine and cosine only gets from -1 to 1, right? So when does it get to 1? So cosine theta only gets to 1 when it's 0, and it only gets to its lowest when it gets to negative I mean go to 180, not negative 180. It's just 180. 180 degrees and 0 degrees, right? So what I usually use degrees for polars though. So we're just gonna teach with degrees, right? So if we have when does 3 pi gets to 0 degrees? It's just that when theta is 0, so that's 3 times 0 is 0. So cosine 0 is the maximum. So you gotta think about it. So you have 5 here, and that's how I usually graph about it. That's the biggest point because 0 is because a cosine of 0 is the biggest, and the lowest point is gonna be sorry. And the lowest point would be when it's cosine of a 180, because 180 is cosine of 180 is -1. So for it to get 180, I have to say 3 theta is equal to 180. So theta has to be 60 degrees. So if theta is 60 degrees, then 3 times 60 degrees is 180, and cosine of 180 is -1. So that gets to -5. So what it tells me is that at so at it will be at 60 degrees, it's gonna be at -5. So what that coordinate tells me is basically -5, 60 degrees, right? So you kind of just look at the graph. So you have -5, you start at the upper side because this is 5, so this is -5. So you go 60 degrees, right? And then based on the graph and how I look at it, we have cosine of 3 theta. Since I know that this is rows, and since this is odd, it must have 3 petals. So it must, and it usually, and the petals are equal distance from each other. So since there's 3 petals, that means each petal has to be 120 degrees from each other, because the entire circle is 360 degrees, right? So if you divide by 3, you get 120 degrees. So each angle has to be 20 degrees from 120 degrees from each other. Because think about it, this is 60 degrees, as I said before, because that's 5, and you guys go 60 degrees. So if this is 60 degrees, and this entire line makes 180 degrees, that means this is 120 degrees, which makes sense, because this is the greatest point to the least point. And now you just have to make another point right here. So if this is 60, then just go 60 more here, and you get the next highest point, which is true because this is 120, and this is also 120. So that makes the petals. So how it usually looks like is that it's gonna make a petal like this, sorry, let me get like rid of the numbers and the lines. And so it has a point like right here, right? So you kind of make like a kind of like an oval, and then like another oval, and then like another oval. You don't have to be really precise about the answers unless like the teacher really wants you to be, or like how the question want to ask you, not just teachers. You basically just want to draw it like that. Like I really don't care how the shape looks, like how precise it has to be. This is the general shape, and that's how it's gonna look, basically. Or let's just take another case. Let's say we have something like r is equal to 4 sine of like um 2 theta, right? So let's make the graph 0, 0. I mean circles, 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 circles. So circles. So we need to make 4. So that's 1, 2, 3, 4. So when is sine the biggest? So in a normal plane, the sine is the biggest. Y sine is equal to y. That's how I remember it. And x is equal to cosine. So if I want a big x, I just need to go in the x-axis, and if I want a small x, I would just go to like a really small right here, or a really big negative. And if I want a really big sine, basically, I need to go to a really top on the graph. So technically, I need to get to that 90 degrees. And if I want a really small sine, I go to a negative 270. And that's how I remember it. So I need, not negative 270, 270. Sorry about that. So if I need to get, if I want a big one, I need a 90 degrees. So theta has to be 45. So 45 times 2 is 90. So at 45 degrees, it'll get, sine is 1. Sine of 45 is 1. Sine of 2 times 45, which is sine of 90, is 1. And then 4 times 1 is just 4. So that's the biggest radius. Because, it, like as I said before, sine and cosine only gets from negative 1 to 1. So basically, I'm going to have the point 445. That's why I know. So I just need to find 1, 2, 3, 4, and I have to go 45 degrees. So it has to go right here, right? That's what I do. I just look for the biggest point all the time. And then the next thing I have to do is that I need to look for the least amount of point. So I need to get 270, right? 270 divided by 2 is 135. Because 135 times 2 is 270, and then sine of 270 is negative 1. So that makes negative 4. So that's negative 4, 135. So 1, 2, 3, 4 on the opposite side, so negative 4. And then 135 degrees, which is just 90 degrees plus a 45 degrees. So 90 and then 45. So it goes right here. Since I know a rose has to have 4 petals and has to be equidistant, right? Because this is 2, and if it's 2, then the property of if it has even, then it's got to be 2 times that. So 360 with 4 petals means that they have to be separated evenly by 90 degrees, which is true because if you make a line right here, you make a line right here. This thing is 135, right? So if this is 135, that means this is 45 because that's a line. And this one was 45 degrees, right? So this is 90 degrees, which is true. So it's always going to be between 90 degrees. So you think about it, that means you have to have 2 other points because there's 4 petals, right? So you got to make another one at the 90 degrees. So 45 here plus another 45 means there's another petal like right here. And then there's another petal right here because of 45 plus that other 45. So you have these 4 petals. And then you just draw the ovals. And that's how you get it. And that's how you get the roses. And that's how like that's why the roses for me are like the easiest to graph. And because you could basically just understand like how much petals you need. You get the highest and minimalist the highest and the smallest point, and you kind of just get a general idea of how it looks. Because usually you don't really need to even do all that work. You could just find like when it's first, like for a cosine, you could just start at 0, that's the highest point, and just have like the amount of petals divide by that number, and then you just make that amount of petals. Or if it's sine, basically you could for sine you just find when it's 90 and you could do it. So you have like, let's say you have something like 2, sorry, you have like 2 cosine of like 2 theta, you know. So basically circle, 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 right? I'm just gonna go 3 circles. We don't need that much. So we have 2 theta, right? So I know cosine of theta is gonna be the best. It's gonna be the greatest at 0. So the maximum point is always gonna be here. So it's gonna be a 1, 2. So it's 2 right here. So that's all right. So that's the first part I need, and I don't need any more other points. So I think about it. There's 2 of them, right? So since it's even, that means it has to have 4 petals because 2 times 2 is 4. So it has to be 360 degrees divided by 4 is 90. So I need so I basically need 3 more other points. So I need to go 90 degrees. So 90 from here is here. And 90 from here to the other side is here. And 90 from here to is here. So those are the 4 petals, and then I just draw it. Sorry, the picture looks bad, but basically these are the petals, and that's how it looks. They're never gonna overlap. Like basically how the picture looks like, it's just gonna look like that. It looks like it's overlapping, but it's just really small. And that's how you do it. Like that's just the faster method, and that's what I use all the time. I'm not really precise with the picture. I couldn't care less of how the picture looks. It just has to have the general outline, and it's gonna work. Or you can just have like 3 sine of like 3 theta, right? And then you just have like 1, 2, 3, 4. You know, draw. Okay. And then sine of theta is the biggest when it's 90 degrees, right? So I need it at the 30 degrees. So it starts at the 30 degrees when it's the biggest. So 30 degrees at here would be 90, would be the biggest at 3. So the biggest will always be that coefficient, which is 3. So it's at 1, 2, 3. All right, 1, 2, 3. And it has to go 30 degrees. Right? Since it's odd since it's odd, that means the petals have to equal the coefficient, which is 3. So it's 3. So it's just 360 divided by 3 petals. Means each of them is like equally spaced by 120 degrees. So I just need to get, since I already have one of the petals, I just need 2 more. So I need to, since this is at 30, right? That means I need to go, that means this is 60. So I just need to make another 30 right here. So another 30 would be like right around here. And there's a 60 here. That means I need to get this 60 right here. So you just make another petal right here. You kind of just think about the general outline. And you kind of have like this general shape. So you have right here, here, and here. And all these are separated by like 120 degrees. And that's how I know it's correct. And it's all at 3. If you want it to be really precise, you could get like a bunch of other points that you know. Like that's why you remember the unit circle, the 45, 45, 90 degree triangle, and the 30, 60 degree triangle. And you kind of just use that in tandem with like the, let's say you have like 4 theta, right? And you wanted to find the 30, the 60, and the 90 degree triangle, right? So 30 divided by 4 is like 7.5. So you find the 7.5 degree, or 60 divided by 4 is 15 degree. You find the 15 degree. And 90 divided by 4, which is like 22.5. You find the 22.5 degree. But usually that's what you like basically do. You want to be really precise. And that's how you like graph. And the last graph that you want to look over is lemniscates. Lemniscates. I don't know how to pronounce it exactly. You have the radius squared is equal to a squared times sine of 2 theta. And r squared is equal to a squared times cosine of 2 theta. For this type of graph, I mostly kind of just memorize it. Like, since these are the only 2 cases, and lemniscates are, like, super weird. Cardioids sounds like a heart. Limacon looks like a snail, and roses, hence the name roses, you have petals, so that's how I memorize. Lemniscates, I really couldn't think of anything to memorize it by, so what I usually do is that the only one that's left is basically how the graph looks. And that's how it looks. It kind of looks like an infinity sign, and that's how I remember lemniscates. So if not the other graphs, it has to be the last graph, which is the weird graph, the infinity sign graph. That's how I remember it. So you have the infinity sign graph. If you have the cosine, it's just gonna look like this. And that's how I just memorize it. Just only 2 cases, so it's not that hard. And then you have the sine one, which is the diagonal one, which is really strange. I can't tell you how to like really graph this, but like you basically actually had to graph it. So what you're gonna do is that, let's see, you have you have r squared is equal to like let's say 4, because that's 2 squared, and then you have sine of 2 theta. So it has to have 2 theta basically in there. And that's how you tell. Because if you ever see anything in the coefficient, it's either a rose or a lemniscate. If it's a 2, then it's a lemniscate. And how you tell between a rose and a lemniscate, basically there's an r squared value. So if you look at roses, limacons, cardioids, circles, and lines don't have an r squared. Or they either don't have an r squared or they don't have an r. They all have r's. They just have r. Lemniscates are really unique because they're the only graph with r squared, and that's how I also memorize it too. So basically, if you want to like, usually what the teachers do is for like every single cardioid, you kind of just like, I mean not cardioid, for every single polar graph, you kind of like make these charts. So you gotta think about it. You gotta have theta, you're gonna have r. So you gotta find out, since they expect you to know like the 30, 60-degree triangles and the 45, 45, they want you to find like when is it 30 degrees, when is it like 60 degrees, and when is it 90 degrees. So you gotta basically look for those. So since in the unit circle, basically you need to look, sorry, you gotta look for the 30 degrees. Of the in the unit circle, there's only a few of them that you need to look at. You need the 30 degrees, the 45 degrees, and the 60 degrees, and then you could go around the circle, which gets you the 90 degrees, and then you could loop around to get you the 120, the 135, the 150, and then to the 180, and then you get the 210, the 225, and then the 240, and then the 270, and then the sorry, let me think about this. 270 would be 300, 315, and the 330, I think. Yep, the 330 and 360, which is the same thing as basically 0. You put 0 here. So basically, find out when it's 0. So 2 theta is 0, and you kind of find like sine of 0. Sine of 0 is basically 0. So 4 times 0 is 0, so radius is 0. And then you have sine of 30, so you want to find sine of 30. So the theta has to be 15, right? So 15 degrees. And then that makes sine of 30. Sine of 30 is basically 1/2. So that would be 2. So radius squared has to be square root 2. And then you have sine of 45. So 45 divided by 2 is 22.5. And then you basically get sine of 45. Sine of 45 is square root 2 over 2. So that would be 4 times square root 2 over 2 is just 2 square root 2. So radius would be square root 2 square root 2. You could use your calculator to find the decimals. And then you get like 60, which is just 30. 60 divided by 2 is 30. And sine of 60 degrees is square root 3 over 2. So that would be like 4 times square root 3 over 2, which is 2 square root 3. And then radius is square root 2 square root 3. Square root 2 square root 3, yeah. And then you just basically do it for like every single point. And it kind of just basically takes a while. And that's basically like how you would do it. And you have like these kind of graphs basically. And that's what you're gonna be doing. See, that's how you do it for every single graph for polar graphs though. And then you kind of like once you have like these points, like what you do is that you kind of graph them. So if you didn't know the way to, I didn't show you the way to like graph the roses. That's basically this is the universal way of how to like do it. So basically you have the points, then if you didn't have like the exact like kind of like idea of how this looks, what you're gonna be like how this looks, you're just gonna put in like those degree values to get the radius, and then you just gonna put them together. Then you're gonna get like you have something like sorry, you're gonna have oops, the graph is a little weird over here, but like basically what it's gonna look like is that you're gonna have a point like this, and then you're gonna find a point, another point, another point, another point, and then it's gonna loop back around like this. Like you're gonna have something like one like 20 degrees, and then like two 50 degrees, and then sometimes it's like in between like you have like 2.5 and then like 30 degrees, right? And then you just put the points in the right place, and then you put it around, and it seems like it's going back around basically. So you put those points in, and then you kind of see the general outline of how you graphed it and the order of how you did it. So you kind of just like, okay, you kind of graphed it this way, and you just connect the points, and then you put it together, and then you get that graph. So it looks like this, or like this kind of graph, basically. So that's how you basically how you do it. You kind of get the equation. You put the degree signs like the ones you know, the 30, 60, and 90-degree triangle, and then you just like go, which is how you gotta remember from the unit circle, from our like the previous video when I talked about it. You gotta memorize those triangles. So and then like the ones I showed before, the 0, the 30 degrees, the 45, the 60, the 90, the 120, the 135. which is just basically the exact same graph. Like, it's just like 30, 45, 90, right? And then, like, from this graph, you just add 30 degrees because you know the 30 degrees with the 90 degrees. So if this is 30, right, then this is 60. And that's how you remember it. And you get 135, right? So this, if this is 135, then this is 45. 40, 45, right? And if you want, and you have like 150, right, over here, then this has to be 30 degrees. And you already know the 30 degrees. So it's just basically keeping track of the negatives and the positive, and you get it right. So you know those special right triangles, so you put those, and then you make this graph. And you do this for like cardioids, circles, lines, limacons, and roses, and lemniscates. And that's basically how you graph like these equations. That's why it's like super tedious for you to like actually draw these graphs for polar, because you have to understand the graphs. Um and then you could do like the lines of symmetry, because like basically let's say you have like this kind of graph, right? And you prove before you like find any points, use the symmetry tests, and you find out that it's symmetrical to the polar axes, then you don't really have to graph like all the bottom points also. Because then as you get like the points, like it'll look, sorry, uh, it'll look like this. So circle, 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 circle. So the general outline is kind of infinity in the right direction. So what we'll usually do is that it's gonna look like, it's gonna draw like this basically. So what you do is that like you know it's gonna work. So if it does something like this, you don't have to really calculate this. I mean, you could you calculate this point, right? And you know after from 0 to 180, because that's all you had to graph, that it's gonna be that's gonna be symmetrical over the polar axes. Then technically you see this graph, you just had to reflect it over the this x-axis, and you just make this portion, and you see reflect this over this one, which is this one, so you get that infinity sign basically, and that's how you do it. So that's why you do it. You get the equation, you find out what graph it kind of. If you don't know what the graph is, then you don't find out what the graph is. So if you get the graph, I mean the equation, the first thing you do if you don't know what it is that you do the symmetry line test. So you find out what points you really don't need to graph, and then you find the special right triangles, and you basically find the exact points. And then if you do know the graph, basically, right, then you're just gonna memorize the equation. You look at the equation, you memorize it. So how I memorize it, lines, really simple. If it's really, really basic, it's the lines. That's all I remember it as. Like theta is like the most basic thing alive. And then you have r sine of theta and r cosine of theta. And that's how I know. Because I know x, y goes to r cosine of theta and r sine of theta. And then you have circles, which you reverse the r's and the a's. Because lines are the only ones with is equal to a. Is the only one. And then you have circles, cardioids, limacons, and roses are the ones that equal r. So I know it's a circle because it has sine of theta is like really the basic one. So if it's a line, it's a that you're calculating. If it's a circle, you're calculating r, and they're both basic. If it's a cardioid, right, it's gonna have the same number basically. For the coefficient, so as AA. So that's the same. The constant is the same thing as the not the constant. If it's not the same, then I have a limacon, and I found out, and I just think about which one's bigger. So if the coefficient in front of the trig function is bigger, then it's gotta be with the loops. If it's not, then it's gonna be smaller than loops because it goes from -1 to 1, as I explained before. And then you have the roses, which is basically with the r, and then you have the coefficient. It's the only one with the coefficient and a single r, and that's how I know. And you just memorize the rules for even and odds to make the petals. And you just know it's equidistance, as shown before. Roses are the easiest. And then you have the lemniscates, which is all you just basically memorize. And it's the only one with the r square value, but it's also with the coefficient. It's not the only one with the roses are not the only one, but roses are the only one with the coefficient inside the trig function with just a single r. And then lemniscates is the only one with the r squared. And then those are like the most basic graphs. There are like really weird graphs sometimes that kind of like sometimes make like weird curves, like some kind of butterflies. But we won't be covering that here because it's not really that necessary. You just, if you understand the basic graphs, the lines, the circles, the cardioids, the limacons, the roses, and the lemniscates, you should be basically fine. So I hope this video was helpful, and thanks for watching, and I'll see you at the next math record.